Namaskar. My name is Dipankar Mandal. I, along with my friend Anupam, Ashikor and Suras, we are going to uh, give presentation in the topic of memory-bounded heuristic search algorithms. So, content is introduction. In this part, I will going to discuss why we should move to the memory-bounded heuristic search. Memory-bound and heuristic search will be discussed by Anupam, and complexity and optimization will be discussed by Ashikor, and applications of memory-bounded heuristic search will be discussed by Suras. So, in introduction, the main issue with the best first search is the memory. So, despite of the effectiveness of star as an optimal heuristic search method, large branching factor, that is the number of child node, the number of child node of a parent node, that is called large branching factor, that is called branching factor, and deep solutions lead to an explosion of memory uses that cripples any modern computer. So, IdeaStar pays for a memory efficiency with increased time complexity. So, in IdeaStar, though memory efficiency is there, as that memory is the linear, but the time complexity is much more than the star. So, aim and objective, the to discuss the heuristic search algorithms that require linear space, and to discuss heuristic search algorithm that efficiently uses available memory without sacrificing the time efficiency. So, in BFS, we know that the nodes are traversed or explored level by level. That's why the time complexity is b to the power d, and the space complexity is also the b to the power d, as all the nodes are will be saved in a memory. So, if we can have a example, so we can see that if the b is equal to 10 and d is the branching factor and the memory requirement 1 kilobyte per node, then the memory will be needed 10 TB, that is 10 terabyte, and the charging will take less than 3 hours. So, we can see that the memory requirement are bigger problem for BFS than the execution time. So, in DFS, so to use the linear search, here LIFO queue is used in the append list. So, if we so time complexity is the same, that b to the power d, but the space complexity is in the linear, that is the b to the power d. Here b is the branching factor and d is the depth. So, we can see that if we can have the example, then we can see that 10 kilobyte of memory, and here in BFS they are needed the 10 TB of the memory. Okay. So, this was the DFS. So, but after that the informed search was came into existence. So, in informed search, some domain specific hints about the location of the goals are needed. So, best first search, I am use an evaluation function fn for each node. Fn provides the estimate of the total cost. So, the total cost, the estimation there we are using, means in informed search we are using a estimation that what could be the means probable estimation to go to the goal node. So, happen consists of a heuristic function denoted by Sn. So, Sn, that the heuristic function is actually the hint. Okay, actually the heuristic function is the hints of the to have the goal node. So, some properties of heuristic function is that Sn is non-negative, and it is problem specific. Obviously, for a specific problem, the heuristic function is the specific. It is different with the some problem. And another one thing is that a heuristic value of goal node is 0. So, in A star search, so A star search is here, if we are using is the Fn, this Fn, the evaluation function Fn as Gn and Sn. So, what is Gn? Gn is the cost so far to reach n. So, if I am in B, so A is the starting node, then 105 is the Gn, means the cost needed from coming from A to B, and heuristic search is the estimation from B to go to G, means the goal node. Okay, so here the S of B is the 30, and Fn estimated total cost of, so ultimately summation of to Fn estimated total cost of the path through n to, means path through n to goal. Here n is B and C, so ultimately Fn is equal to Gn plus Sn. So, the properties are S star is optimal and complete. So, optimal and complete if the branching factor is finite. So, definitely the branching factor should be finite. If the branching factor is infinite, then we cannot then the algorithm will not complete, and also optimal too. So step costs are some greater than sum of a positive value, that is we are here epsilon we have taken and some positive value. So Sn is admissible and monotonic. So the admissible. So why we are discussing the heuristic things here? Because the heuristic function is related to the space complexity, means the space needed, the memory needed for the heuristic function, means heuristic search. So here we have to discuss about the heuristic function in some details manner. So disadvantages is, means disadvantages of S star is it keeps all the generated nodes in memory, means A star usually runs out of space long before it runs out of time. So here the problem is almost similar to the BFS. So at worst case it behaves like BFS only, as it is going to keep all the generated nodes in memory. So at worst case it have exponential, that is O b to the power d. Here d is the branching factor and now b is the branching factor and d is the depth. So big O of b to the power d space complexity. So almost is it can behave as in case of space complexity as the BFS. So heuristic function. So we have to discuss the heuristic function in some details manner, because there is some relations between the space and time complexity with the heuristic function. So a heuristic is admissible if for every node s of n is less than equal to s star of n, where s of n is the heuristic function and s star of n is the actual cost to reach the goal state from the n. So an admissible heuristic never overestimates the cost. So concept of good heuristic, here good, the term I am using, it is also a problem specific. So time and space complexity depends on the good quality of heuristic, and this will see in next slides in details. And heuristic is applied to guide the search towards the goal. This is the actual work of the heuristic. So for example, here this is a band, so from start to 0 to some the actual cost. So here a star n is the actual cost, and one heuristic is s1 of n and s2 of n. This s1 is the heuristic function 1, s2 is the heuristic function 2. So here we can see that s1 is less than equal to s1 is less than s1 is less than s2. So here the closer the heuristic function to actual cost is considered as better the heuristic function is. So here S2 is closer to the S star, so that's why S2 is better heuristic than S1. So we can say that S2 n is more informed than S1 n. So here we can means conclude that every node seen by A2 is also seen by A1. So the space explored by A2 is contained in the space explored by A1. From this example, we can see that the S1 and S2, these are heuristic functions, that is both are admissible and means that is less than means S star, means the actual cost. So here the search space created by the S1 is bigger, and the search space the created by the S2 is smaller than S1, means S2, the search space created by S2 is contained in S1. So why? Because the S2 is closer to the S star. So more informed heuristic is more focused towards the goal. Search space become narrower, and but unfortunately we don't have the perfect heuristic function. So we try to look for the as good as possible. So here good is again problem specific. So we can say that so using a better heuristic we can have we can have better result in terms of the space complexity. So the time and space complexity are also depend upon heuristic search. So here I said also, because the heuristic is not only the factor, here the other factors, so the way of searching. So that like in depth first search and breadth first search, the way of searching also is a very big factor. So but the heuristic function is also a very good factor for the in which the time and space complexity depends. So better the heuristic function is, lesser the amount of the space is needed. So ideal star search, heuristic search can perform as bad as BFS if a good heuristic is not chosen. We have already discussed this. So basic idea to achieve the similar benefits with iterative deepening search for heuristic search. So while finding minimum cost of the path, memory grows only linearly with the depth of the goal. So we know that. So perform a DFS is iteration with the cutoff value of F cost. So what is the problem with IDStar? So heuristic function was introduced to show that we can have a search space, which is means we can have a search space so that the search space is focused to the goal. But in IDStar, it is seen that the f value is only used to create the boundary, and the within the boundary some means the DFS means depth first search are done. So if it is not found the goal, so again the boundary will increase with the next step, means increased in the next level with the next means minimum f value. So there also only the means DFS are done, but ultimately idea is not exploit the heuristic function so efficiently, means so well, because it is heuristic function is used in the fn so that the boundary can be created, not it is not like focused means to the goal like other best first algorithm. So this is the problem of idea star, it is more like the uninformed search. So next, the recursive best first search algorithm, it mimics the best first search means A star search with the linear space. How it does not means store means all the nodes it have explored, it just delete it and go to the next best node. So similar to the recursive DFS, but not continue indefinitely down to the current path. Keep track of the f value of the best alternative path available. If current f value is exceeds the alternative f value, then the backtrack to the alternative path. Upon backtracking, replace the f value of each node along with the path with a vector value, the best value of children. And RBF is optimal like A star. Space complexity is BD, means B is balancing factor, D is depth, like ID star. So it's linear, and the time complexity depends on the heuristic function. And there is a problem, that is a thrashing problem. This will be discussed with the example in next slide. The simple example of RBFS. So let us assume S is the start node, and 60, 70, these are all the f value of the nodes. So among these nodes, means among these nodes, so 40 is the base node, and the so it will be go to the closed. So it will be the close to the closed, and 60 is the second best according to the RBFS. So after 40, we'll have three nodes in open new node, 45, 50, and 61, 45, 61. So among them, this one is the base node. So this one is the base node. So this will go to the closed. Now the second best will be 50. Okay. So second best will be 50. After the so this is in the closed, so it will be in the open. 48, 40 is 48, 70, and 60. This node. So but and now this will be in the closed, and this will be in the closed, and thus this will unsensed. The second best is the 50. So now after exploring this node in the open 55, 70, and 70, so it is seen that no, the second best is the there is no any node that it is less than 50. So this will roll back from this point. Okay, so among them 55 is the smallest, so this value will be 55 now. This value will be 55 now, and among them, among these nodes, again 55 is the smallest. So now this is the 55. Now this is the 55, and then this will be the 55, and these nodes will be deleted. So in this way, the RBFS saves the memory. So in the S star, what will happen if there is a pure S star? Then this will not be deleted and just start exploring from 50. But here this node will be deleted, and now exploring from 50. So in this way it will be means in this way this will be in this way this will be traversed, explored. But again, if there is a condition like here we have seen, so if this is 50, so next best is 55, we know that. So next best is 55, next best is 55. So again, after seeing some greater means larger value node here, the condition like this side, so again this will move to this side. So ultimately it can have, if the good heuristic is not chosen, that this can be a there is a means some situation that the algorithm go to in the back and forth, this way and this way, this way, this way. So ultimately this is called the thrashing problem. So but the RBFS is giving the RBFS is optimal and giving the linear time complexity. So next part, the memory bounded heuristic search will be described by my friend Anupam.
Hello everyone, my name is Anupam Boythakur. In this presentation, I am going to speak about the memory-bound heuristic search algorithm. Till now, Dipankar Mandal has already stated about the shortcomings that has been there in the search algorithm. Whether we use the heuristic or we don't use the heuristic, the search actually the shortcoming is related to the memory. Sometimes it's go down exponential part. So for that, to mitigate that shortcoming, memory bound is kept on the searching algorithm that uses a heuristic. The two algorithms that I am going to discuss in this particular presentation. The first algorithm that I am going to discuss is about the SMS star algorithm, also known as simplified memory bound A star. It was proposed by Stuart Russell in the year of 1992. Basically, the concept of keeping the restricted memory while keeping the search algorithm is came back in around 1989 in the paper called Heuristic Search in Restricted Memory. That paper was presented by Parthapratim Chakraborty sir, Sujoy Ghosh sir, Orup Acharya sir, and S.D. Deswarkar sir. And after around 3 years, the simplified version of that particular algorithm is proposed by Stuart Russell that I am going to discuss in this particular presentation. This is the algorithm that was presented in the paper presented by Stuart Russell. There are two main things that has been prominent quite here is about a max t and the used one. Max state about the how many maximum number of nodes that can be there at a point at any point of time in the searching part in the memory, and used at any point of time how many nodes are there in the memory. So maximum keeps a limit about till how much node is allowed to keep in the memory, and use keep a counter as how many nodes are there in the memory. So let's suppose this is the graph I have taken just for simplicity. We can take this as a graph, and this is the start node, and followed by three successors of the particular start node. Let's start with the open. So I have to keep the open in the open list as in the open list, and use equal to 1. Since right now it is in the open, so nothing is so this particular line is not be executed. And since I have to find the leaf cost that has been there in the open, so since there is only one node, so right now this is the base node and this is not the goal node, so this should not be executed. And I have to find the success of the base node. So this is the base node. There are actually three possible paths that I can go for, but I have chosen the path of chosen A. There is not mentioned implicitly about which path to choose, so we can take any of this one path. I have taken the A path. After taking this particular node, this become the successor of the node, and I have to find this successor f value of the particular successor. That is the maximum of the f value of his parent, and the path cost and the summation of the path cost and the heuristic. This is actually g value, and this is I have to sum up both the two and the f base value. So whichever is the maximum, I have to take that particular value and that put it in the f value in the particular successor. After that, if computed based, uh, computed is in I can explain with this particular graph. Suppose at any point of time there are two successors of A, B and C, and let's suppose B and C has already been traversed, and A at the time of again looping this, suppose A come as the base node. A come as the base node. Now that particular node becomes as the computed node because the all the successors of the particular node has been traversed. So there is no unexamined successor left out. So that particular node becomes the uh, computed node, and then it will call as a procedure called backup end. But in this case, there are two more nodes are left one, so and I will not be executed this backup procedure. But if in case backup procedure executed, then I have to find the least cost between the successors, be f cost of the B and C, then the least one of it and update to its A value. And if it has a parent, then I have to increment that one also. I have to change update that value also. But in this case, it is not there. Then you have to increment the used one. So use has been incremented to 2. You then if used equal to max, suppose there are 5 nodes, that is the maximum 5 nodes are allowed in the memory. Then since then this part will not be executed, and at last the A node will be put in the uh, open list. And after that, again I have to take the minimum of these two. So suppose A S is the minimum, and again I have to take the one of them B and C I have taken as B, find the F value, increment the use value, and again the C value, and increment the F value, and use this 4. In this way, this part will be executed. There are three prominent things that has been there in this particular algorithm. The first thing is about it generate children one by one. I generate children A, then find the then in the second iteration find the B, and then third iteration find the C value. And simultaneously generate one children, and it find the f cost of one children. and then it check whether I have to decrease the memory or not, and whether at per iteration I have to call the backup positor if required, if A is competent. And if it is competent, then it might happen that all the parent node app value might be changed because of calling this backup positor. So these are the things, and these are the also different that differentiate between the SMA star and SMA star plus algorithm that I am going to discuss at a later part. Now I'm going to discuss a simple example by taking an example how this particular tree has been solved. They are the E and I, the optimal path to part these two goal node E and I, how SMS star will find it out. There are 9 nodes overall. So I have taken about maximum allowed node as 3. First of all, this is the start node. Since A is the start node, I put the start node here, and used equal to 1. Used equal to 1. Then I can take any one of this. Empty is not been executed. Empty is not open is not empty. So from these two, I have just taken as B node. I can go for C also. I have taken here as B. Then I have to take the maximum of this 11 and 15. 10 plus 5 is 15, and maximum is 15. 5 where is it? 15. So the F value of the successor, that is the successor node, if it is 15, then all these things will not be executed because neither A is computed nor it is one is, suppose I have to increment the one value as 2, neither 2 is greater than 3, so it will not be executed, and this particular B node has been there in the successor node. After again I have to find out the minimum between the 11 and 15. 11 is the lower one, so I have to take the 11 part and hide the successor. I have taken C as a successor and find the F value. 11 and 13. 13 is the highest one, so this is the 13. Now at this point of time, A is in the base node and C is in the successor list. So I have to check for computed base. At this point of time, A is computed since both the successor has been traversed. So backup procedure will be calculated, and in the backup procedure, the minimum of between the 5, 15 and 13 will be there as F value as A. So 13 is the minimum one, so 13 the F value of A has been updated from 11 to 13. And uh, since there is no parent one, so it will stop here, and then I have to increment the used one. Right now, among these three, 13 both are 13 one, but I have to take the next iteration the least deepest one. So this C node has been chosen as the one, and I have to find the successor of the C node. There are two possible paths. I have taken for H node. Taking the H node here and find the F value of the H node. Among 13 and 28, 28 is the highest one. So I have taken the F value of F1 as 28. At this point, the use has been implemented and used equal to 4. And at this point of time, this particular use is greater than equal to 4 because 4 is greater than equal to 3. So this has been executed. And among these three, actually, it seems that 28 is the highest one. But now, right now, 28 is not there in the open list. Only A, B, and C is the open list. 28 has been just been there in as a successor. So among these three, I have to take because it is stated, I have to take the highest efforts that are there in the open. So this one is the highest one, so I have to remove this one B node. So removing this B node, remove it from parent successor list. So from parent successor list it has been removed, and they are in a parent open list. So in the parent open list. After that, I have to decrement the use value. So U is equal to 3. And insert that H in the successor in the open list. So right now A, C, and H are in the open list. After that, among these three, this is the lowest one, so the best lowest one. So only one node is there that you can go, that is the I node, and increment the value of 24. Right now, this is the, as I have said, this is the base node right now in the base, and this is the successor. So if computed base is again true because both the nodes has been traversed, so now backup pointer has been called. So similarly, as I've done in this particular point, so 28 from 24, I take the minimum out of it. So 24 is the minimum one, and among then I have to again, since backup parent is there, so I have to backup this one, and from taking the backup, A value will be updated to 15, as minimum of 15 and 24 is 15. So like that, backup pointer will be computed. After now, the use will be incremented to 4, and 4 is again greater than equal to 3. So among these three, among this A, C, and H, the highest one will be eliminated, and highest is actually H. So this node will be eliminated, and actually eliminated. And there in some materials that I have found, they have replaced this 28 actually with infinity, because what they have said about this, because it is not possible to get a goal node even if they are after H, because I have taken a memory limit as 3, even at max it goes to 3 node. So if H is not the goal node, and after that it is not possible to get a goal node. So some of the many things they have replaced with an infinity. After that they have curled that node and put it in the uh, open list of the parent node. But in the algorithm proposed by SMS star, it is not mentioned to take the infinity part. So I have gone with the algorithm that has been there. So I have replaced with it 28. That is the f value of that particular node that has been curled, and use value decreased to 3. So at this point we are in this stage. Now the the thing is that I have the minimum of 15, 24, 24 is a 15. So I have to take the successor, that is the 15b1, and the value is equal to 15. Now the use value is again 4, that is greater than the max value. So right now from A, C and I, that is the maximum one is the 24. And the thing is that I is also the goal node, but it thought that there is, first of all, it's not an open list, not empty, and also it can think that there is A has forgotten a node 15, from that part also the goal can be possible. So it has not been terminated because of these two reasons. So now in this case, the three nodes, from these three nodes, I is actually the highest one. So I have to remove this I node. After removing this I node, the value is actually not been updated. So it is said that if necessary update. So it is not necessary to update the value of this one. So use value is 3. After that, among these three, 15 is 15, both are the lowest one, but I have to take the deepest one. So deepest is B. So from the B, there are two ways: either go with D and E. I have gone with D. So app value has been updated 24, and then since computer based, there are one more computer based not been executed. Use value is incremented to 4. Again, 4 is greater than equal to the max value. 4 is greater than equal to the 3 that we are taking. So this part will be executed, and from this 15, 15 and 24 I had to remove someone. So this is the highest one. So C will be removed, and this C will be removed, and it will, since the 24 will be kept here as it is forgotten the node, it will keep there in the successor node. Since, and after that the use value will be decreased to 3. After that, the 15, I have to take the minimum of 15, 15, 24. 15 is the minimum. Then I have to take the successor of it, E. There's only one way, E is there. At this point, again, this is the base one, this is successor one. And I have to update the value of 15. So from to the minimum, since backup was just been executed. So from 24 and 20, the minimum is actually the 20. So 20 has been 20 has been updated as the f value of B. Again, since it is as a parent, so I have to again from the 24 and 20, this 20 has been updated. And similarly, after doing so this is the graph, and after that the use has been incremented as 4. Again, the use is greater than equal to max. So use is greater than equal to max. So I have to remove the best one. So best the highest one. So from 2020 and 24, this was the actually highest. So it has been removed. So at this point we are in the 3, and decrease the use value as 3. So we have made the criteria. Now at this point of time, if we take the best one, and the best amount is the deepest is E, and this all has been computed. So particular one after one, all the once we remove from that particular open list, and at the end we are getting the base goal node, and this is the result that will SMS try algorithm will give on this particular graph. After that, there are two theorems that is given by SMS star. The first one says that it will grant an optimal solution even if the max cost is at least large as the number of there is the optimal path. Suppose if in this case, suppose as far as E node, this is the actually the this is one under goal node, and suppose 10 this I say as 5, and this is suppose 4. So we have calculated this value as 24, this value as 20, and suppose this value is actually 19. This goal node is 19. This one is the optimal. But if I keep at max value as 3, then it will never go to this particular node, because only 3 nodes we can keep there in the memory at any point of time. So it will not go to 3. So it will give an optimal solution. 20 will give it solution, and 24 also give a solution, but optimal is 14. So it will give an optimal solution provided the max is at least as number of nodes there in the optimal path. So at least it has to be 4. It can be more than that, it can be 4. And if it is more than that, that is max is larger than the number of nodes generated, then SMS star behaves identically to A star, because difference lies in the SMS star generates one by one generates B, then it generates C. Then but and also if max is larger than the number of nodes that A star generated, then just both are identical to each other. These are the two theorems that are proposed in the particular paper that we have taken from. Then came in SMA star plus algorithm, and it came in 2017 in the paper given by Lovengra J and Jeng Sung. They have said that enhanced the SMA star in the SMA star plus. I'll not take an example, just I will put it down as where the differences lies from the SMA star algorithms. The first differences lies in it generates all the success of the node. That is, suppose this is the starting node, and these are the three nodes that successor of the particular start node. So what it does is that it will start with the used one, as it will start with s as used equal to 1. Then it generates all the three simultaneously, all the three elements simultaneously. After generating the three nodes, it will increment each of the fn values of a, b, and c, either using this or this or this. It will increment the value of it will update the value of a value of all the three nodes, and accordingly it will increment the used one. So after that, it will check whether it meets the criteria of having the maximum number of nodes in a memory or not. If suppose I think the memory equal to 2, then it is used is 4 equal to 2, so this will be executed. Actually, this is u, this is m, so 2 is greater than 4, so it will be executed and one of the nodes will be curled. Let's suppose m values of is 11, 12, and 13. There's also a culling function that I am going to discuss in the next slide, but as of now, suppose this is the 13 one, this is the highest node, so it will be curled. So now used will be equal to 3. Till now also 3 is greater than 4, so again it will be executed. One of the nodes will be removed from here, curled. So let 12 is the curl, then it remains with used equal to 2. Now 2 is greater than 4, that is not true, so it will not be, and this it will come out of the while loop. So it says that there are three possible things, actually three differences that lies is that it generates all successor. In the SMA star it generates one by one. Since it generates one by one, it updates the value of fn of that one by one, but here it generates all its successors and update all its fn values. Then it checks whether it meets the particular memory requirement or not. If it is not meeting the memory requirement, then it will keep on curling until unless this particular condition is not been satisfied. This is actually the curled word slip. Uh, this is the function that they are using. They'll do while curling the things, and they will use the word list first from this particular safe curling heuristic. This is the particular equation that they are suggesting. They will find a leaf node that having the maximum cn value. That is the maximum cn value they will find. Fn value, dn is actually the depth of n from the starting node. There are particular depth it is having, and e is given the Euler's number. They will find the leaf node that having the maximum cn, and they will compare with the base of fn below the base node, and if that two matches, they will curl the second worst leaf of cn. That is, if c1 is the highest one, then curl the c2 if this condition matches. And the difference lies, there's also one difference is that it update f of only one node, because it for the every time it is called, if this condition matches, it will not be called in worst leaf. So if it is called in worst leaf, suppose in the SMA start there is a procedure called the backup procedure. In the backup procedure, if it is called, then it might change, it happen that it execute in the loop. So it will keep on going till the parent is not, fn value is not being executed. But here only one time the fn value is updated for every time it is called. So these are two differences that lies in the SMS star plus. So at the end, these are three differences I have given here. There are also some differences are also there. Just like suppose expansion is not if one time in SMS star plus. Like that, if expansion happening, then the updation of SMS star is also happening more than one time. Like that, SM in SMS star also. So, but these are three prominent differences that I already discussed about the backup expansion, and this they have given in the paper. This is less efficient than the more efficient. So this is a thing. So at the end, we have discussed about the SMS star and SMS star, both how these things are work. The next part will be carried out by Asikur Rehman. Thank you.
Hi, this is Asikur Rahman. I am going to talk about the complexity and optimization of this topic. In the previous topic, Anupam has talked about the SMS star algorithm and how they work, and they also talk about the curling heuristic function. In the SMS star algorithm, actually it provides a step-by-step example with a memory limit, and each new iteration it expands a node and remove the old sleep node. In the complexity and optimization part, we are first going to talk about the implementing the open list. In the implementing the open list, as you can see in the diagram, The most optimal search methods are concerned with only with the minimization of the F cost, and that is analogous to the parameter of SMS star. By contrast, the most function minimize the F cost when selecting the next node to be expand and maximize the culling heuristic function when selecting a node n to cull. The original SMS star used a binary tree. This approach provides a log x time to insert, remove, and pop the base successor, where x is the number of nodes in the tree. However, since this tree must maintain all the nodes with successor instead of only leaf nodes, the worst case time to curl a leaf node is x, because we must search nodes in descending order of f cost until a leaf node is found. Further, this structure does not support a curling heuristic other than the Cn is equal to Fn. So, this ordered by ascending f cost and containing all nodes not fully expanded is used to select the next node to expand. A second queue ordered by descending Cn and containing only leaf node is used to select the next node to call. This approach provides log x time to select and remove a node from open to curl a list. By maintaining two lists, removal and addition must be performed on both lists, resulting in worst case 2 log x time when all nodes in the open list are leaves. Additionally, the position of each node is each queue should be tracked for efficiency. Further, we can expand this node and we can see that if the memory limit is never exceeded, this open list has the same performance as the A star algorithm. In the theoretical performance, we can see that the greatest strength of SMS stars come from the ability to set the upper limit bound on a space. So, when SMS stars clearly has the worst case space complexity as M, where M is the memory limit. Assuming that the M is greater than equal to Z, as M is greater than equal to G, where G is the number of nodes generated, SMS star function as A star with the complexity of B to the power D, where B is the branching factor of the problem and D is the depth of the solution. When uh, M is less than G, the SMS star becomes difficult to analyze theoretically as performance depends on the how many nodes must be re-expanded. So, in the best case, when no nodes are re-expanded, worst case performance B to the power D, but space complexity is M. So, clear advantage is given that M is less than B to the power D. Every node that are re-expanded adds to the cost of SMS star plus gives a worst case of G that is greater than equal to B to the power D. However, since the size of the open list is M, as you can see, that the cost of adding and removing elements from the open list is less than A star when M is less than G. So, in the empirical analysis can show that when even when the M is significantly less than G, so SMS star performance is minimally affected by the M, where M is the memory limit. We can talk about the complexity, completeness, and the optimality. So here we can propose here we see can that two lemmas and two theorem are stated, which states about the SMS stars, which also SMS star plus that this which proves the completeness and the optimality for SMS star plus when the sufficient memory is available. What is the lemma one told us that f cost of removed nodes are maintained to give a correct lower bound on the cost of solution path through unexamined successor of a node with unexamined successors. Means that the when the unexamined successors are there, you have to find the you have to find the bound of the you have to find the lower bound of the f cost that you have to find. The lemma to that SMS star plus always expand the node that has the best lower bound on its unexamined successor. You have to find the best lower bound on the unexamined successor so that the SMS star plus going to work. What is the theorem one told us about? That SMS star plus is guaranteed to return the optimal solution given an admissible heuristics that we have to given to the function, and the memory limit that should be d plus 1, where d is the depth of the optimal solution. Also, the theorem to tells about that SM star plus behave identically to the star when memory limit is greater than the number of nodes it generates. The last part is the application part, and it will be talked about. It will be delivered by the Mr. Suraj.
As this Dipankar, Anupam, and Ashikur, they have given the brief introduction, brief idea about the SMS star algorithm, that how it really works. Now we will see that the with the help of this application that how this SMS star algorithm works. So we'll take this the very basic problem in the artificial intelligence, which is very well known problem, which is the missionaries and cannibal problem. So in this missionaries and cannibal problem, what is happening? The problem statement is given as the three missionaries and three cannibals. They are on the left side of the river along with a boat that can hold at most two peoples. So find out a way to get everyone from the left side of the river to the right side of the river without leaving any group of missionaries on either side of the river or on the boat outnumbered by the cannibals in that place. So in this problem, what is given? So here, these are the three triangles are given, which are defined as the three missionaries, while the three red circles are given, which are the cannibals. So what we need to do, we need to move these missionaries and cannibals in such a way that they can be moved with the help of this boat on the right side of the river in such a way that on either of the left or right side that the number of missionaries has to be greater than or equals to the number of cannibals. So this is the constraint that we need to satisfy. We'll see more details into this problem. So as we learned in the class that every problem has to define a particular state. For this particular problem, the state can be defined as MC. So where M is the number of missionaries while C is the number of cannibals on the left bank of the river. The initial state is given as 3 3. So here the three missionaries and three cannibals, they are on the left side. So the state can be defined as 3 3. Now what we need to do, we need to move this in such a way that we need to reach the goal state, and the goal state is 0 0. It means that there is no any missionaries and cannibals left on the left bank of the river. So the goal state is given as 0 0. And now in order to perform this, in order to reach from initial state to the goal state, there are some invalid states also. So what are those invalid states? That when the number of missionaries and cannibals on either banks of the river is greater than 3 or less than 0, that means that doesn't satisfy our initial state and the goal state. Then the second invalid state is that the number of missionaries is less than the number of cannibals on the any bank of the river. That means that it doesn't satisfy our constraint. The constraint is given as that the number of missionaries has to be greater than or equals to the number of cannibals. If this constraint doesn't satisfy, then it will be our invalid state. Now moving to this, so as this constraint is given, so what we need to do, we need to perform some actions so that we can move missionaries and cannibals from left to the right. So now we'll see. So basically there are 5 possible actions that can occur during the various states in the problem. So what are those 5 possible actions? We'll see now. The first action is that the one missionary moving from one bank to the another. The state is given as 1 0. The second action can be one cannibal moving from one bank to the another, and it can be given as 0 1. The third possible action is that one missionary and one cannibal moving from one bank to the another bank. So we'll see what is this, what is basically happening in this particular action. So here this is the initial state where there are three missionaries and three cannibals. They are on the left side. Now what we'll do, we'll move one missionary and one cannibal from left side to the right side with the help of this boat. Now the state will change from 3 3 to 2 2 because we have moved one missionary and one cannibal on the right side. So we're left with two missionaries and two cannibals. So the state is given as 2 2. So this is basically this is the action that is happening. This boat is helping to move this missionaries and cannibals from left to the right and from right to the left. The fourth possible action is two missionaries moving from one bank to the another, while the fifth possible action is two cannibals moving from one bank to the another. The state is given as 0 2. So this some of the actions they doesn't satisfy our constraint. So those are the invalid states also. Now what we need to do, we need to find out the optimal path in such a way that we can move from initial state to the goal state. And in order to reach the optimal path, we need to follow the heuristic function. So for this particular problem, the heuristic function is given as c raised to the power of n plus ml raised to the power of n divided by 2, where these parameters are mln is the number of missionaries on the left for node n, while CLN is the number of cannibals on the left for the node n. Now we will see the different states and how this problem is moving from its initial state to the goal state. So the initial state is given as 3 3 and the corresponding goal node function is 3. So as we discussed that there are basically 5 possible actions are there. So if we'll expand this particular node, then it can be given as something like this. So the initial state is 3 3, while it has reached when we will expand this particular node with the help of this first action, then we will get the state as 3 1, where this 3 1 is the invalid state. Why this is the invalid state? Because it doesn't satisfy our sorry this is the valid state. Then this is the 1 3, which is the invalid state. Why? Because here it doesn't satisfy our constraint. The constraint is that this m has to be greater than or equals to c. So this doesn't satisfy our constraint, that's why it is given as the invalid state, and the invalid states are shown with the help of blue square. Now the third possible node is 2 2. Then the fourth possible is after expanding this particular node, after performing fourth action, we will get it as a 3 2. Again here, and the fifth, after performing the fifth possible action, what we'll do or what does it mean is, like, if we will move one missionary from the left to the right, then we'll get the state as 2 3. For this particular problem, if we will move one cannibal from the left to the right, then we will reach the state 3 2. But again here the 2 is less than 3, so it doesn't satisfy our constraint, so this state is invalid state. So I will remove this. Now the possible states are the 3 1, 2 2 and 3 2. We'll further expand this particular nodes. Now what we'll do, we need to find out the heuristic values at this particular function. So I will calculate. The heuristic function is given as something like this. The heuristic function is given as the state at the particular node raised to the power, this is the second state, so raised to the power 2 plus the state on the right side is 1, so 1 raised to the power second divided by 2 is equals to 5. So I will get the value for the heuristic function as 5, and after that if we'll calculate the function at this particular node, then I will get this like 3 plus 5, that turns to be 8. Now at this particular so whenever I have moved this one missionary and one cannibal from the left to the right, then I will reach this state which is 2 2. And for this particular 2 2 state, if I'll calculate the heuristic function, then it can be given as 2 raised to the power 2 plus 2 raised to the power 2 divided by 2, which turns to be 4, and if I'll calculate the goal function at this particular at this particular node, then it will turns to be 3 plus 4, which is 7. After this, if we'll calculate the heuristic function for the 3 2, then it will turns to be 6.5, and this 3 plus 6.5, that turns to be this 9.5. Now what I'll do, I will further this is the possible state. I will further expand this particular state, and the after, like, this is the 3 1 state. If I'll move from the left, if I'll move one cannibal, if you'll observe here, this for this particular path the heuristic function value is 25.5, or and for this particular path it turns to be 24.5. So As per this SM star algorithm is there, what it will do, it will find out the minimum function value, and for this the minimum function value is 24.5. so what it will do, it will follow this particular, so it will follow from this initial state of 3 3 to 2 2, and then it follows this particular path and it will reach to this particular state which is 3 2. Now here we have defined this m is equals to 11, so that it means that we haven't visited till now 11 nodes. As per this SMS star algorithm, what it will do, it will uh, reduce the number of, sorry, it will eliminate the number of nodes after reaching the 11 nodes. Now if I'll further expand this 3 2, then it turns to be 1 2, which is again invalid state. Then it turns to be 3 0, 2 1, again which is invalid state, and then it turns to be 2 2. We have already visited over here, and then this is the 3 1, which is again. Now for this 3 0, if I'll calculate this, the heuristic function value, then it turns to be 14.5, and if I'll calculate this function node, then 24.5 plus 40.5, it turns to be 65. After this there is one more path, this, which turns to be 3 1, and the corresponding heuristic function value is 41, and if I'll calculate the function value at this node, then it turns to be 65.5. and now if I'll compare this, so this is the 65 and this is the 65.5. As per this SM star algorithm is there, it will choose the minimum path or the minimum function value. So what it will do, it will choose this one. So this, the optimal path will turn after this 3 2 to 3 0. It will not go for the 3 1 because it has the higher function value. Now after this, what we'll do, we will further this expand this 3 0 node. Now here this, the function value at this particular, the last node, it was 65. If we'll further expand this, we'll reach to the two states, the 3 1 and 3 2. Now among this 3 2, it is already visited state, so we can neglect this. And if I'll find out the heuristic function value for this particular 3 1, this is the at state 5, so 3 raised to the power 5 plus 1 divided by 2, it turns to be 122. Now if I'll calculate the function value at this particular node, then it turns to be 187. It means 122 plus 65. If I'll so this is the optimal path. Now if I'll further expand this, I'm going to get the 4 different states. The first one is the 2 1, which is invalid state. Then the second turns to be 1 1, which is turns to be valid state, and then 3 0, which turns to be already visited state in the last slide, and it turns to be 2 0, which is invalid state. Now what we'll do, we'll calculate this, the heuristic function value, and if we'll calculate the function cost at this particular node, then it turns to be 188, and we have only left with only one path, so this is the optimal path. Now we will further expand this node, and the 5 possible states are possible. So among this, the first one is the 2 1, which is invalid state. Then it turns to be 3 1, which is already visited state, because we have already visited over here. After that, it turns to be 2 2, 1 2, which is invalid state, and then 1 3, which is again invalid state. So we are left with only one possible solution, which is 2 2. Now if I'll calculate the heuristic function value, which turns to be 128, and the goal function, which turns to be 316, we're left with only one path, so this is the optimal path. After this, if we'll further expand this, there are 5 possible nodes are there. The first one is 1 2, which is already visited state. Then the second one is 0 2, then the 2 1, which is already visited state, and then 2 0, which is already visited state, and then the 1 1, which is invalid state. Now we will further expand this, or what we'll do, we will find out the heuristic function value for this particular node, and it turns to be 128, and there is only we are left with only one possible optimal path. And if I'll calculate this, the function cost at this particular node, then it turns to be 444, and this is the optimal path that we are going to follow. After this, if I'll further expand this, then the four possible states are given, which are given on this next slide. So here this the function cost value is 444. If I'll further expand this, I turn to be the state turn to be 1 2, which is all invalid state, then 0 3, then the 2 2, which is already visited state, and then 1 3, which is again invalid state. Now if I'll calculate the heuristic function for 0 3, then it turns to be 9841.5, and if I'll calculate the function cost at this particular node, then it turns to be 10285.5. And this it will follow because we left with only one node, so it will follow this particular optimal path. After that, if I further expand this, then it turns to be 0 2, and which is already visited state on the last slide, so we can neglect this, and then we're left with 1 0 1. And if I'll calculate the heuristic function at this particular node, then it turns to be h is equals to 1. So the function cost value is 10286.5, and this is the optimal path that we are going to follow. And now what is happening? So this one is the 12th node. This is the 12th node, and now as per this SMS star algorithm, what it does that if it utilizes the maximum memory, then what it will do, it will use the curl function. So what this curl function doing is, like if you have already visited nodes and if they have the maximum value, maximum function value, then it will curl those nodes, means it will eliminate those nodes. So this is from the first slide. So this one is the first node that we have visited. Now we are no more, that is not occurring, or it has the maximum function value, and it is not along the optimal path, so we can neglect this. So what is the memory used by this node is now forgotten. So what we are utilizing the maximum memory, or the maximum or the memory, or like if we'll say this, that till this the A star algorithm and SMS star algorithm, they are same, but now after this it's changing. Like when it visited the state 12, so what it will do, it will when it visited the node 12, then it will eliminate those nodes which has the maximum function value, and it will eliminate those nodes. So what I will do, I will eliminate this particular node, and then I will store the information for this particular node. Now, so for this 0 3, it will eliminate this particular node, and then for the 0 1, it will eliminate this particular node. Now if I'll further expand this, then I'm going to get the 5 possible states, which is 0 2, which is already visited state, then the 0 3, which is again already visited state, then the 1 2, which is invalid state, then the 1 1, which is the possible state, and then the 2 1, which is already visited state. So now we are left with the only one path. If I'll calculate the heuristic function as it is 1 1, we are going to get the heuristic function value as 1, and I will get the function value as 10287.5, and this is the optimal path. Now whenever it will store the information for this, so what it will do, it will eliminate the information stored in the initial states, and which has the maximum cost, so it will forget this particular node. And in this way it is utilizing the maximum memory, and the memory consumption by this SMS star is very less. So if I further